So, welcome to your first module here at Salford. So, the module is Electricity, Matters and Light, but I thought since it's the first lesson, I thought it'd be good to give you an introduction to my research, because it'll give you an idea of what my expertise is and where I'm coming from. So this introduction is something I usually give on the first lesson for the first years. This one's a little bit longer, and the reason is something quite exciting has happened in relation to some line of research I'm looking at. So I'll come on to that in the end. So I've done quite a lot of different aspects of physics research throughout my career. So I've worked at lots of different universities, different research groups, doing really quite different aspects of solid state physics research. So based in the UK, in Japan. So this is really quite a varied bunch of research topics. I'll just give you an introduction. So one of the things I did, this was actually when I did my PhD at the University of Salford, was looking at femtosecond laser written waveguides. So it's all based on technology related to glass. So I was working in a research group that made a very special type of glass. It's gallium platinum sulfide glass, or called it GLS. So this is a chalcogenide glass, which is different to the standard types of glass that you might be familiar with, which are usually based on oxygen, like silicon dioxide is the glass you find in window panes. So chalcogenide glasses are glasses that are made substantially of sulfur, selenium, or tellurium. So this is a sulfide glass. It's based on sulfur. It's really quite difficult to work with because it will react with oxygen and moisture in the air. So when you're melting it, you have to keep it really dry. But it's got some really interesting properties. So one of these is it's got a very high non-linearity. So this means its optical properties change depending on the intensity of light that is shone on it. Whereas standard silica glass has very low non-linearity. Right? You shine a really bright light onto a bit of silica glass, like the glass you find in a window, it doesn't really change its refractive index or its absorption or anything like that. Whereas chalcogenide glasses have this very high non-linearity. This makes them really useful for making optical devices like switches or amplifiers or any of these devices that could make the internet run much faster would work really well with a glass with a high non-linearity. And what I looked at was trying to make structures in the glass that can guide light. So if you're going to make some sort of optical devices, say you like got an optical microchip or something, so that's taking channels of light and moving them around the device into different places, into different devices. So a little bit like a microchip, but using light instead. So you need some way of channeling the light. And one way of doing that was with making a femtosecond laser written waveguide. So we take a block of glass, just a polished block of glass, and then we take a very special type of laser called a femtosecond laser. And this femtosecond lasers produce the shortest anything by man, right? So there's no man-made thing that is shorter than the pulse of light you get from a femtosecond laser. So to put it into context, a femtosecond compared to a second is shorter than a second is compared to the age of the universe. It's a really, really short instance of time. So it's 10 to the minus 15 seconds. So what this means is that when this pulse of light is shining, the instantaneous intensity is incredibly high. So you can get all these interesting non-linear effects occurring. But the average beam power is quite low. Like you can put your hand in it, and it doesn't do anything, as far as I know. I've put my hand in it before, 20 years ago. It's fine. Nothing's happened to it. There's nothing growing out of it. But when you shine it in the glass, then you can have these interesting non-linear effects going on. So if you imagine I've got a block of glass, and if this is my femtosecond laser, so there's a beam coming down, then if my hand was the block of glass, then we're just focusing. There's a lens here to focus it, and the focus spot would be somewhere inside the glass. So that's where you get the really high intensity, and this is changing the structure of the glass. And then we just translate the piece of glass along like that. And then you get a channel going through the glass, and that can guide light because it's changed the refractive index inside the glass. So you can then shine a laser beam, and it will channel through that bit of glass. So these are some figures from a publication on this. So these are some different waveguides. So this is what the end face looks like if you look through a microscope, the light shining from the back. So you get a bit of a funny shape, which is to do with the way the light interacts with the glass. And then this image on the right is what we call the guided mode. So this is when we shine a laser down it, and this is what the shape of the laser is going through the glass. So we can get a nice what's called single mode guidance here. So there's only one path that the light can take down the waveguide here. And the waveguide shape changes really dramatically with the pulse energy. So we can vary the energy that's in each pulse of light that we're using to make the waveguides. And well, you can see the different shapes you get in the microscope images here, but this is what the refractive index looks like. So you can measure the refractive index on a cross section. So for low pulse energies, you get like a little positive index, and then as we increase the pulse energy to make these waveguides, we get this funny two-peak shape. So we've got this kind of dip in the middle, which is like just this part. So what I think that is where we've actually vaporized the glass. So we've made a tiny explosion, if you like, in the glass, and it's actually resulted in negative refractive index there. That's when we get the really high pulse energies. And like I said, this could be useful for building three-dimensional photonic devices, so like an optical chip that's got various devices on it, and it's light being channeled. Come in. Find a seat, please. Another thing I look at is resistive switching devices. So these are devices that can change their resistance, and they're useful as memory devices. So memory in computers, basically ever since computers were invented, has been divided into storage and RAM. So RAM is the memory that the computer is using at any particular time to carry out calculations on. So it's data that can be accessed really quickly and written really quickly. So as a processor is crunching through numbers, it needs somewhere to store those numbers and access them very, very quickly. And that is what RAM does. So RAM chips, the data can go back and forth to the processor extremely quickly. The trouble is, it's volatile. You pay a price for that. It's volatile, which means that when you switch the power off, your data goes. Whereas storage, which is traditionally used hard drives or solid state drives, then this is the type of memory that can store data in a non-volatile way. So if the power goes off, your data is still there, but the price you pay for that is that it's much slower. So hard drives are incredibly slow compared to RAM. Solid state drives are a bit faster, but still nowhere near the speed of RAM. So for a long time, people have been wondering whether you could build a universal memory, so a type of memory that does both. It's got the non-volatility of storage, so your data's still there when the power goes off, and it's got the speed of RAM. And a new technology has actually recently been developed by Intel. They call it 3D Crosspoint, and it uses chalcogenide glasses. So it's actually a little bit of chalcogenide glass, a thin layer of chalcogenide glass in these devices, and they switch between a glassy and a crystalline state. And the glass and the crystalline state have different resistances, and that is how you store your binary 1 or 0. But what I've been looking at is a completely different mechanism for doing the same thing, but with chalcogenide glasses. Because as well as being able to switch between a glass and a crystal really easily, which is a really useful property of chalcogenide glasses, they can also permit the diffusion of metal ions through them really easily. So if you just deposit a layer of metal on top of a chalcogenide glass, those metal ions will actually diffuse through there. So one way we can exploit that is to build what we call an electrochemical metallization cell. So if we've got a layer of chalcogenide, so imagine this is layered up, it's like a cross section of it. We've got an inactive metal on the bottom, so something like platinum or gold. Then we've got a layer of chalcogenide, and then the active metal. So silver's a good one, it diffuses a lot in these glasses. And then if you apply a positive bias to the top electrode, you can force even more of those ions to diffuse into the glass. And eventually, once you get so much silver trying to dissolve into this glass, it precipitates into a metal again. So it's dissolved as silver ions, and then at some point there's so much that you get silver metal depositing on the opposite electrode, and then that will actually grow as a filament. So you get a tiny thin filament of metal growing through the glass, and eventually it makes a contact with the top electrode. So now you've got a metal bridge, and you get this dramatic change in resistance. So in this state, we've got a very high resistance. Once we've got the metal filament contacting the two electrodes, that's a much lower resistance, and then you can reverse it. So you can apply the opposite bias, so a positive bias to the bottom electrode, and then you'll dissolve that metal filament. So you can go back and forth between these two states. And a few years ago, I thought, okay, maybe I can try it with this glass I've been working on, this gallium lanthanum sulfide glass. So I gave some to a project student, gave him that basically, just some silica glass with a transparent conductor, and then a thin layer of the GLS glass on top, and said, okay, go and make a device, just evaporate some silver and some copper and maybe some other metals on there. And he did that, and then went back and tested them, so put them in a device to measure the electrical properties of them. So he did what we call an IV sweep, which is where you sweep the voltage and measure the current. And this is actually, I think, the very first measurement he did on his project, and it basically showed almost ideal resistive switching. So you start here at a low voltage, a high negative voltage, right? So we're not causing any ions to diffuse, so we've got hardly any current flowing. And you increase it, and we get a positive voltage, and you get a sudden jump. It's exactly what we expect when we get this metal filament being formed. So you get a sudden jump in current. Now we've got a really low resistance. Keep going up, we've still got the same resistance, and we've still got the same gradient on this glass. Go down, and then at some negative bias, we suddenly get a drop in current. So that's where we've broken that filament. So it was almost ideal what we'd expect for this device. And then that was actually published in a really prestigious journal, the work that this project student did on these assistive switching devices. What we found is it was actually the fastest chalcogenide electrochemical metallization cells that had ever been reported. Our equipment didn't work fast enough to measure the speed of the device. It could only say, oh, it's less, it's switching faster than 10 nanoseconds. Something. We couldn't actually measure it. So as far as I know, that's still the fastest that we can get for a chalcogenide metallization cell. So another thing I've been looking at, again related to chalcogenide glasses, is making what we call N-type chalcogenides. So chalcogenide glasses, many of them are really semiconductors, so they're a bit like silicon in that they conduct electricity relatively well, and they can conduct it really well if you add impurities to it. But they have this strange phenomena that they're all normally P-type, and people couldn't change them to N-type. So if you wanted to build some electronics using chalcogenide glasses, you need some way of making some of it N-type. Right? So if you're going to build any transistors or diodes or anything using this glass, which could potentially then be used to make some optical computer, then you need some way of changing the carrier type. And I figured out a way of doing it using bismuth implantation. So implantation is the technology that's used in the fabrication of microchips to get impurities into the silicon. It's impurities that you need. And this is some graphs from the publication, which is in Nature Communications. So as we increase the dose, so the amount of bismuth we're implanting, we get this reversal in the sign of what we call the Seebeck coefficient. So this is just telling us, so this is P-type, this is N-type, and then we managed to get N-type for the first time, anyone had ever reported it back. We also built a device, so this is a diode. We've got some N-type here and P-type here, and essentially responded to light in the way we'd expect. So this was some really important work that had been done on chalcogenide, so it's now known how to make an N-type. Also looked at bismuth doped glasses. So this is taking glasses, well basically any type of glass. I looked at a whole range of glasses, chalcogenide glasses, oxide glasses, phosphate glasses, pretty much every glass I could think of, and put a little bit of bismuth in, because something really interesting happens when you do that. So it can give off light, so it can emit light. So if you shine a laser on bismuth doped glass, it will give off light at different wavelengths, and you can measure the spectrum of that. And it gives off lots of emission bands, so lots of wavelengths that cover what's known as the telecommunications wavelengths. So these are the wavelengths of light that go down optical fibre. So this is really important because it could be a way of making a way of amplifying the signals. So a way of amplifying more of the signals that go down optical fibre, so you could get a lot more data down optical fibre than currently goes down there. But no one actually knows what bismuth centre gives the emission. So by bismuth centre, I mean what type of bismuth is it in the glass that's giving off the light? Like when you put bismuth in, is it a bismuth ion? Is it bismuth 1+, 2+, 3+, 4+? Is it two bismuth ions stuck together? Is it bismuth metal? Is it a cluster of bismuth? Nobody knows what it is. So this is what I've kind of been spending most of my research career looking at, trying to understand what actually gives the light, what bismuth centre gives off this light, and then how could we build some useful optical devices like amplifiers and lasers using this. So this graph here, it looks a bit complicated, and that's because like the emission from bismuth doped glasses is pretty complicated. So instead of showing some emission spectrum this is a contour plot just showing these are the different excitation wavelengths. So if we change the colour of the light that we shine on it, and then this is showing the spectrum along here. So really looking along here is absorption, and along here is emission. So it's showing two things at once. So it's just showing the complexity. You get all these different regions here corresponding to absorption that's giving off emission at this particular wavelength. What you can see, there's some correspondence between these very different glasses. So this is a sulfide glass, this is an oxide glass, and this is another type of oxide glass. And one thing I wondered is, we don't really know what the bismuth centre is that causes the N-type conduction in chalcogenides. So you implant with bismuth, it changes the carrier type. We don't really know, again, is that bismuth 1 plus, 2 plus, 3 plus, bismuth metal. And I was wondering, are these two phenomena related? They're completely different phenomena, like the impurities giving off light, or the impurity changing the electrical characteristics. You'd normally think of them as being completely separate, but I was wondering if they were the same, related to the same bismuth centre. So in this publication, I kind of went over some of the evidence that suggested it was actually the same bismuth centre that caused the carrier type reversal and the luminescence. That was published a little while ago in Optics Express. We've also looked at carbon nanotube devices. So carbon nanotubes are incredibly thin tubes made of carbon. So they're on the order of a few atoms wide, but they can be relatively long. And again, they're semiconductors, and they're one-dimensional in terms of conduction. So electricity can only go in one direction. It can't. It's not like a bulk conductor where current can flow in 3 dimensions, go up or down or sideways. It can only go along the nanotube. So we call it a one-dimensional semiconductor. They've also got ballistic conduction. So normally when you send carriers down a conductor, they're bumping into the charges. Or they're bumping into the atoms that make up that conductor and scattering off them. And that's what gives you resistance. So carbon nanotubes, they're not superconductors, that's something different, but they do have this ballistic conduction where electrons can travel down them and not scatter off any of the carbon atoms. But you can build electronic devices out of them. So you can build transistors and diodes, and this is what I did, a research post in Japan where we're building field effect transistors using carbon nanotubes. So we used the same techniques that are used in the fabrication of microchips. So photolithography, wet and dry etching, so that's getting rid of a layer either using some chemicals or some reactive gassing. Sputtering, this is a way of depositing a layer of some material. CVD, that was chemical vapor deposition, that's how we grew the carbon nanotubes. So we actually used alcohol to grow them. We have a small amount of pure ethanol, and then if we heat up our substrate, the piece of silicon we're growing them on, then with just the right conditions, then you can grow these like long strands of nanotubes. And also evaporation, so that was to deposit the metals. So photolithography is this technique where we put a layer of photosensitive material, thin layer, on top of the piece of silicon, and then expose it to the pattern that we need our devices to be, and then we can use basically the same techniques that are used in photography. We develop it so we can You put it in a developing chemical which gets rid of the bits that weren't exposed to the light, and then we can build up patterns like this. So this, I was actually looking for some good microscope images of the devices I made, and I got hundreds and hundreds of them, but they're all of devices that didn't work. Because you see, when you're building these devices, you're trying the different processes, and more often than not, it doesn't work, and the device doesn't come out quite as you want it. So I wanted to keep the pictures of them and to show what went wrong. So this is like the closest I could find of a device that works, and it's not. You can't. It's not complete. I haven't shown all of it, right? So it's got 4 contact pads here. So that's where you put your pins on, and then these bits here, they're the source and drain. They're the bits of metal that actually connect to the nanotube, and then there's a layer of insulator on top, and then these are the 2 gates. There's actually got 2 gates in there that we can apply voltage to. And this is what it looks like in an electron microscope. So these tiny little thin things here, they're individual nanotubes that are bridging the gap, and these are what cause the device to work, right, those nanotubes. So the devices are relatively big, but the width it needs to be is only the width of that nanotube, which is a few atoms. So it's potentially it could be tiny. Also, because they've got ballistic conduction, it can be really fast. So like using silicon, the clock speed of the processors is limited to like 3-4 gigahertz. That's just down to how quickly electrons can move through silicon. I don't know what it would be if you had a computer made out of nanotubes, but it'd be a lot higher. I'm guessing sort of hundreds of gigahertz. And these devices were also optical devices as well, so they respond to light, so we could get photocurrent out of them, shine light, we could measure some current. They'd also get light, so we apply a voltage to them, get current flowing, we can get light coming off. Okay, right. This is the bit I really wanted to talk about. So, kind of my main line of interest in research is in quantum computers, or related to quantum computers. And I'll just give you a quick introduction to the main technologies that are being used to build a quantum computer. So you might have heard of quantum computers being talked about, maybe not really know what they are, what they're all about. But quantum computers are they're built of what we call qubits. Instead of a bit that we get in a classical computer, a quantum computer is built of qubits. So a qubit is just something that can be in a quantum state. Right, and this is a very different state to a classical bit, which is 1 or a 0. So if we've got something in a quantum state, there's a lot of strangeness to do with quantum mechanics that changes the properties of that. So if you have a qubit, so a quantum system that you're using as the basis of your computer, then you can put it in a state that is both 1 and 0 at the same time, and any mixture in between. So really the difference is that we'll have to introduce a little bit of quantum mechanics here, but if you've got something a quantum system that can be in 2 states, so the simplest quantum system is something that can be in 1 state or another state. So for example, a single electron has a property called spin, so it can be spin up or spin down, right? And if you measure it, you'll measure either spin up or spin down. But before you measure it, then it's got a wave function, what we call a wave function. Right, just give a Greek letter psi. and it's some certain amount, call that alpha, the up state, plus some certain amount, call that beta, of the downspin state. So don't get scared by the strange looking notation that we've got here. So this side, this just means we're talking about a wave function. So something that is described as a wave. It's not in one state or another. It's got this wave-like property where it's two different things at once. So for our two-state system, we've got two numbers here that describe what's going on in this system. Whereas when we measure it, we only need one number. Right, so when we measure the state, we've just got either spin up or spin down, like a 0 or 1. Whereas when we've got this, what we call the superposition of states, there's two numbers that describe it. But the great thing is if you start adding more qubits, then if they're what's called entangled, then they're described by the same wave function. So you can add more and more qubits, and they're all the same quantum object. So what that means is that the number of these parameters that you've got to describe that wave function goes up as 2 to the n, right? If you've got n qubits. So, I mean, you can, if you had 2 qubits, then you've got the states. You've got up, down, down, up, down, down, up. So you've got 4 states. So you've got 2 to the power 2. And if you go 3 qubits, it just blows up. The number of these numbers that you need to describe this quantum state blows up massively. So this means that if you have 300 qubits, right, let's put that into perspective. I remember a computer called the ZX81. My dad had one, it never worked. It had 1K of memory, and it could do basically nothing. This ZX81, it was from like 1980 or something. So it basically had, well, 1K, so that's 1 kilobyte, so it's actually 8,000 bits it's got. It was useless. It could do nothing, right? If you had a quantum computer with 300 qubits, the parameter space, so the number of these numbers, I don't know what that is off the top of my head, but it's more than there are atoms in the universe. So if you could build a classical computer and somehow use every single atom in the universe to represent a bit, it wouldn't have the number of parameters, it wouldn't have this parameter space that a 300 qubit quantum computer has got. Trouble is, right, there is a catch to this. When you measure it, you break, the wave function collapses, and you can only measure 300 parameters. That's if it's working perfectly. So the price you pay is that it's probabilistic. So you can do some computation in this massive parameter space, but when you do the measurement, then it's some probability of what was going on in that parameter space. But it's still incredibly useful. You can still, in theory, do computation that a classical computer could never do. Like problems that involve like computations where you need to go through every possible solution. So there's lots of really difficult problems where there isn't an analytical solution. You need to go through and crunch every possible solution. And these can be done by quantum computing. So I'll just introduce the main technologies there are. So the main one at the moment is superconducting qubits. So this is using a superconducting circuit, and these are now up to, I think the record is now like 50 qubits. That doesn't mean we're getting near to this state, right? They've still got problems with errors and things. So they're not it's not a perfect 50-bit quantum computer. But you can actually use these online. So if you Google IBM Q experience, you can actually get access to IBM's superconducting quantum computers. I think you can get up to they don't let you use the 50 qubit one. I think you can get like a 16 qubit one or something. They can't do anything that classical computers can't, but it's still interesting to play with them. Main issue with this, though, as far as I can see it, well, firstly, these need to run at very low temperatures, so like millikelvin temperatures. So they're in what's called a dilution refrigerator. It's a really large and expensive refrigerator that can get to within a few thousandths of a degree above absolute zero. They're also quite bulky, right? So you can actually see some of the structures on this chip. The superconducting circuits that you need to build the qubits out of are fairly large. Another thing you can do is trap ions. So it's possible to get an individual atom in a vacuum, and you can trap it, usually using a laser beam. So if you shine a laser and you've got a really strong vacuum, you can actually capture an individual atom at the focus spot of a laser beam and hold it there. And these are really good. These are some of the best individual qubits you can get is in trapped ions. So you can have some of the longest coherence times, so it will stay in a superposition of states for a really long time, and you can get them to interact really strongly with each other if you get two of them and bring them close together. So some of the parameters that we need for building a quantum computer are really good for trapped ions. But again, the scaling up is really difficult. Right? If you imagine you want to get hundreds of these, how are you going to trap hundreds of atoms and get them close enough to each other, all floating in space? As far as I can see it, this is, again, it's something that can't really be scaled up. Another technology, so this is one that I thought until recently might actually be the technology that would end up building a large-scale quantum computer is donor impurities. So these are the impurities that you have in silicon. So they're the same impurities that you've got in your phones and your computer that change the carrier type to p-type. Like you need some phosphorus in there to change the silicon to p-type, and that's what makes the transistors in your phone work. But this is looking at individual phosphorus atoms on silicon. So those two spots there that you can see, they are individual phosphorus atoms on a silicon layer, and then the rest of this stuff is just the structure that's needed to control them. And this is a 2 qubit device, so we've got two phosphorus atoms here that were entangled together, and this was quite a recent demonstration of what could be done with individual atoms in silicon. So I could see a way of, in theory, you could scale that up. You get enough atoms into your silicon and control them individually. It could be a way of building a really large-scale quantum computer using that. Another really promising technology is quantum dots. So again, this is in silicon, but what it uses is the phenomenon of quantum dots, where if you confine electrons into a small enough space, then it behaves as a quantum system, so like an atom or something. Right, so if all the atoms are confined into a close enough space, then you've got a system that is quantum, so it can be in one state or another state, or one state and a number of other states. So you can do that either with crystals. You can get tiny crystals that are quantum dots, but they're very difficult to build devices out of. But another way you can do it, which is really neat, is in a device. So if you've got like a thin strip of silicon, and then you put some metal gates on top, then you can apply voltages to those gates, and that confines the electrons in that bit of silicon. So you can have quantum dots inside a device here where it's defined with the gates. So again, this is using the technology that's kind of already understood, like building tiny electronic devices in silicon. And again, this is a 2-qubit device using a gate-defined quantum dots. So then another technology, so this is one that I thought was a bit of a non-starter. This is photonic qubit. So this is using photons as your qubit, so an individual photon of light. Here you can build an optical circuit, so something that can guide light down it, and then you can get entanglement in quite a neat way. So you can just put a photon through a beam splitter, and then the knowledge about which path that photon took through the beam splitter is erased. Right? So as long as you can generate a single photon on demand, so you can say you can press a button, get a single photon coming out, and you've got a detector that can pick up a single photon, then once that goes through a beam splitter, the universe then says, okay, you didn't know which way the photon went through the beam splitter, so it actually went both ways. And you've then entangled that photon into both states that it went, the possible directions that it went down. And then you can build up a more complicated system of beam splitters and channels of the connections between them, and you can build up, in theory, a complex quantum computer. But again, I thought my impression of this was that this was limited, but even more strongly than the superconducting qubits, because to scale, there's no way of scaling this up to like millions of qubits, right? Because these are channels of light, and it has to be relatively big, and there's lots of problems of the light leaking in. So I thought that was a bit of a non-starter. But I'll just tell you a bit about the work I've been looking at. So I've been looking at an element called erbium in silicon as a building block for a quantum computer. So erbium is the element that allows the internet to work. So without erbium, the internet just wouldn't run, right? Because it gives off light at exactly the right wavelength that goes down optical fibre. So in order to send light a long distance, you put a little bit of erbium in a length of optical fibre, and then you can excite it with a laser, and then when you get some weak signal, say a YouTube signal from America is coming down the optical fibre, it's almost died out, say halfway across the Atlantic, and then it goes through a little section of optical fibre that's got erbium, excited erbium in it, and then you get identical photons coming out. So you get the stimulated emission. So when these weak photons come along, they stimulate the erbium to emit some photons that are identical, and those go on further to stimulate more erbium, so you can massively amplify a signal. And there's no electronics in there, it's doing it really quickly, and that is what makes the internet work. So erbium is critical for that, and my idea was to try putting it into silicon. So silicon is the material that microchips are built out of. So I thought, okay, if we can get erbium into silicon, maybe it's got some useful properties that could be used for building a quantum computer, because it would also work at this wavelength that we need to send light down optical fibre. So any sort of communication between computers could then be enabled with that. So we've had some recent publications. So we recently showed for the first time that you could couple this to a superconducting resonator So this was published recently, so that could be useful if you've got a superconducting quantum computer and then you want to then send some of those quantum states over an optical fibre, then you could couple it to the erbium and silicon. We also showed the first measurement of the coherence time, so this is the time that the erbium is in a superposition of states, this special state that you need to be in order to build a qubit. So it's the first measurement of that, and that was, and then we've also done a lot of characterization. So did a lot of interesting measurements to show exactly what type of erbium we've got in the silicon, because that wasn't really understood. And that was published in a Nature group publication recently. So that's what I've been working on for a few years now. But quite recently, I heard about a company called PsiQuantum, and this was started by a professor from Bristol who was looking at photonic quantum computing, and it's been valued at $3 billion, so it's had some investment that's valued at $3 billion. So it had like 500 million investment, which put the value of the whole company at that. And they haven't made anything, it's just a technology company that's got this idea of how to build a quantum computer, and they're looking at building a photonic quantum computer. So something like this, something a bit like this, right? But they think they can build a 1,000,000 qubit quantum computer. So they're going to leapfrog everyone else who's looking at sort of 50 or so qubits and go to a 1,000,000 qubit quantum computer. So at the moment, the quantum computers are kind of just toys, right? They can't really do anything useful, but a 1,000,000 qubit quantum computer could really do something useful. And it uses silicon photonics, so it's got light travelling down waveguides in silicon at the telecommunications wavelength, 50 nanometers. So it's the same wavelength of light that erbium in silicon gives out. They use this special encoding, so they use what's called dual rail encoding. So don't worry about the details of this, I'm still trying to figure it out, but it means that if you've got a qubit represented by a photon either down one rail or another rail, then you can have what's called heralded loss, so you can know when you've lost a photon, which is incredibly useful. But the main thing that they've done to realise this 1,000,000 qubit quantum computer is they're not trying to build a bigger computer. So they said, okay, we've got this network of photonic devices on our chip, but we want to build a big entangled state. So what they've done is they take a photon, like one photon that's going in one of these waveguides in their photonic circuit, and then delay it, so send it through a loop of optical fibre. It takes some time, and it delays, and then this photon then goes back into some other states that have been set up on that photonic quantum computer, and then those two states are entangled. So if you keep doing that over and over, then you build up your entanglement in time. So as well as being entangled in space, you've got a few photons being set up on this network on the chip. It's also entangled in time, so that's how they're going to get their 1,000,000 qubits. So they look really serious about this. The amount of money involved means that a lot of people who know about this really think this could be the way to build a large-scale quantum computer. And they've actually got one of the main foundries. There's only a few tier 1 foundries, so factories that can build the top of the range microchips. There's only like 3 or 4 of them in the world, and one of them, Global Foundries, is building this quantum computer. There's no other foundries are trying to build any quantum computer. Right? They don't have the time, right? It's cost billions to set up these factories to churn out the processors that go in your phones. So they haven't got time to mess about with research, but they must think that this is a good enough idea that they're willing to build it in their factories. So out of all the things that could potentially build a large-scale quantum computer, this is actually the most relevant to my line of research in erbium, because erbium in silicon, I've been looking at 1.5 micron light, so 1550 nanometer light, so this is the light that they're using in their quantum computers. So I'm still trying to figure this out, but it could potentially be used as a memory in these computers if they want to. As far as I know, they've got no storage in there. They're not trying to store any quantum states, but potentially a bit of erbium in silicon could store these quantum states. So that's why this is now stretched on much longer than I normally do in these lessons, because there's something really quite interesting has happened in this line of research. So let's finish that there. Okay.